We are honored to have three distinguished professors to present their research today. And each speakers will have approximately 60 minutes for your speech, and followed by 5 minutes answer and questions. And if you want to have more time for the QA sections, and you can slightly speed up your speech. And our first speaker is Professor Wenxuan Zhong, and let us welcome Wenxuan Zhong to present her speech.
Thank you very much. First, I want to extend my sincere thanks to all of you for taking time to attend this talk in such a hot summer afternoon. I hope that my talk will just keep you guys awake, actually, at least for an hour, and so that you won't just fall asleep because of this humid weather here. Okay. My name is Wenxuan Zhong, and 中文翻译钟文轩。Actually, I'm a UG athletic professor, athletic association professor actually in Department of Statistics. Okay, and I came from Georgia, and I served University of Georgia for roughly 10 years already. Before that, I was in the UIUC, and so I was there as an assistant professor for almost 6 years. So that's pretty much like my short bio. And today I'm going to introduce the Graphon CV method that my lab developed for the network models, and especially to select the network models. Our method basically tackles one of the important challenges in the network modeling field, particularly on how to evaluate and fine-tune the estimate or fine-tune the estimation approach to avoid overfitting, such that our model can be generalized across the diverse dataset and the contents. Okay. So the network study, we all know that become more and more important recently, right? And many people using the social media, and so in the social media, basically we construct the social network, right? And for example, in the Facebook and maybe in WeChat, and so people have connected, or people become friends and through this social media. And another important type of the network is a biological network. For example, the protein-protein interaction network, right? So how the protein, they work together and to conduct certain biological functions, okay? And we also have the brain image data to construct the brain network, okay? So how the neurons and the neurons, they work together, and to process the information or learn actually from the outside environment. We have all those different type of networks, and especially recently, and people using the deep learnings, right, is a neural network, right? And that's become more and more popular in the artificial intelligence recently. And so mathematically, what is a network? So those networks actually, just in the social sense or in the biological field, but mathematically, how we represent the network, it's basically a square represented by a square matrix. Okay, the square matrix is called the adjacent matrix. Okay, and each row of this adjacent matrix just represent the entity. Okay, so for example, in the social network, it just represents the number of person. Okay, and the column also represents the person. Okay, and if a person and a person, they are friends, and we use 1 to denote that they are linked together, and there is an edge. okay? And if a person, if two persons, okay, they are not a friend, and then we just use a 0 to denote that they are not a friend at all, okay? So it's just a square binary matrix. So this is mathematical understanding of this like network. Okay, so why we want to use the matrix or JSON matrix to represent the network? Because through this JSON matrix and the many search algorithm or many functions that can be completed. So for example, like if we can use this like a JSON matrix to do the path finding, okay? So finding the shortest path and along all the different like transportation or something, okay? And for example, this is a flood washer algorithm, right? And we can also use this JSON matrix to measure the centrality. Okay, so like what is the center of the network? What is the hub of the network? Okay, and what is the degree betweenness and also the closeness? Okay, of those like different group of peoples. And we can also use this to the community detection. Okay, so for example, like we have the network, but maybe one of the network and they are just contractors, and the other and they are just top 500 companies employee. Okay, so they basically can be divided into the different communities. Okay, so this job is a community detection. Okay, so this is why we want to have the JSON matrix. Okay, and there are actually many methods to model those JSON matrix, because as what we said, that the JSON matrix is mathematical representation for the network, right? So to model the network, essentially just model this JSON matrix. Okay, now let's take a look of the how those like model just evolves over time. So the simplest model is called this Ardo-Rini model. Okay, so which assume that for all the like entries in the matrix, JSON matrix, they are follow a Bernoulli distribution. Okay, and the Bernoulli distribution, however, have a common probability, underlying probability, which is a p. Okay, so the key thing here is the ij means like the connection between the entity I and the entity j. Okay, so this specifically for the ij's link. However, this p does not depend on ij anymore. Okay, so p is common for like all different ij's. Okay, obviously that this model is overly simplified the situation, right? So why we just assume that the people just have the same probability to be friends with each other? Obviously, some of the people, they are characteristically like more like each other, right? And they are more similar. They are more likely to be friends compared to others that who you don't know at all, right? And then people come up with a little bit updated model, okay? And so this is a popular model called the stochastic block model. So in the stochastic block model, it's no longer just assumed that there is a single P. However, they assume like two different probabilities, P in and P out. P in is basically just within certain group of peoples. So the connecting probability is the same, okay, within this group. And the P out means like if they are not in the same group, and the connecting probability follow a different Bernoulli distribution, okay? And compared to the Ardo-Rini model, and this actually muchly relaxed this like a constant probability like requirement, right? However, it's still not flexible enough. The most flexible model is actually we call the Graphon model. Okay, so what is a Graphon model? For the Graphon model, we basically assume that for the ij's link, they follow a Bernoulli distribution with the probability Pij. So the Pij is specifically for the ij's link. Okay, and this is very flexible. Okay, and so if this Pij actually, have this can be categorized into two different numbers, P and P out, then this reduce to this model, right? And if the Pij is common for every Ij, and so reduce to this model. So this is a pretty flexible model. However, the difficulty for this model is you only have one observation to estimate the Pij, because for the network, for ij's like a link, you only have one observations. You don't have a replicates, right? And in statistic or even in probability, so if you only have a one link, you cannot quantify the stochastic errors, okay, or we call it the measurement errors. You don't have a power or degree of freedom to estimate this one, okay. And then we have a trouble. So we have a flexible model, but we cannot estimate it. So, why bother to have this flexible model, right? And then to make this model estimable, then we have to put some other constraints, okay? And this constraint is we further assume that the Pij actually follow, equals to this form. F here is a smooth function, okay? And so by putting this like a smoothness constraint here, okay, so we basically tell people that when this I and the j, they are close, and they can't be any number between 0 and 1. They have to be close, if this like ij close to each other, and the Pij have to be close to, to each other, like close enough, okay? And so here we basically put this like a smoothing constraint here, okay? And the ui and the uj here are the hidden variables. So ui basically is uniform distributed like numbers from the interval 0 and 1. Mu j is also like a number from 0 and 1. Okay, so we have two hidden ones here, ui and uj. And we also have a constraint f have to be smooth. Okay, so this part here is a majority just put a constraint here. Okay, because if you only look at this function here is not identifiable at all, right? Because mu n and mu j is unknown, and the f is also unknown, right? And so basically this thing here is not identifiable, so you won't be able to estimate the f at all. However, what you can have is this one here, Pij. If you don't care like what f really is and what ui uj really is, okay, and you put them together, you can estimate this Pij. So this one here, this constraint here basically tell you that the Pij have to have some constraint, have smoothness constraint here, okay? And the Graphon model is the most flexible like network model. Okay, and so why we want to basically use a Graphon model, because it can be used for many like real world practice. So for example, like they can be used to construct the recommendation system, right? And so if you purchase anything on the web or make so for example, maybe watch movies from the Netflix or something, right? And after you watch one movie, and the website will just recommend another one to you, right? And so this is basically for recommendation. So why Graphon model can be used for to make this like a recommendation system? That is because if you look at the model here, Graphon model is not only used for estimation, but can be used for prediction, right? And so basically by default, this one here, this constraint here, okay? So once we have the uij and we have another like once we have the Pij here, and we are not only have the Pij hat, but we define the neighborhood around this Pij, right? So within the neighborhood of the Pij, because of the smoothness constraint, and the other Pij won't be too much difference from this Pij here, right? So it basically can make a prediction. And because of this, and there is another very important application for this like a Graphon model, which is the drug repurposing. So drug repurposing basically is a pretty popular topic, and in the actually pharmaceutical pharmaceutical research. So the drug repurposing basically means for some drug, originally it was designed to treat certain disease or certain like symptom or conditions, right? And later on, if we found out that it can be used to treat other disease, okay? And so this is a drug repurposing. The nice part for the drug repurposing that it can just significantly shorten this like drug development time, because if you want to develop a new drug and you have a 3-phase like a clinical trial, right? And the phase 1, then you have to first prove that the drug here actually is the toxicity of this drug, like the drug is not toxic, right? But if doing the drug repurposing, because like you already approved this drug for some other treatment, right? And so naturally, the toxic part of this like a drug has already been passed. Okay, so it can just shorten the time. So we have a Graphon model. We know that this is a pretty flexible model. Then how to estimate the model, okay? For the model estimation, and actually the popular approach, because I mean naturally we can think by putting this like a smoothness constraint, basically assume that within certain neighborhood and the probability of two entities to link together, this probability won't change too much, right? And within this like certain regions, okay? And naturally we can just use this like a neighborhood pooling approach. Okay, so we first define the neighborhood here, and we assume that all the link within this neighborhood basically follow the similar like follow the similar Bernoulli distributions with the same p. Okay, and then we can just use this mean, the law of large number. So by just the proportion of the links, and using this number as an estimation for the p in this like a small neighborhood. So it's more like if you are doing the, if you are working on the time series or maybe stock price prediction project, and you probably know the 5-number average, right? So if you just want to, smooth the stock price, what you did is you take a 5 days price, this window size, and then you take an average of the 5 price. And then like this, like a window move on and get the estimation for each day's like moving average price. So similarly, this is very similar to that approach. Okay, and then now the key thing is how to define the neighborhood. So within the network, like which link or which like entity is a neighbor of, are neighbors with each other, because this is a dependent data. It's not like you have an ID, so anybody can be within the small neighbor. So dependent data. So key thing is how to define the neighbor. And one of the approach is the sort and the smoothing approach. Okay, so within this approach actually was published in the 2014 SAML. Okay, and for this approach, they basically sort the degree of all the different nodes. Okay, so for degree basically means how many connections for each node it can have. Okay, so sort the degree of every node, and then we just based on the sorting results and define the neighborhood. And of course, for this one here, we have a hyperparameter, the neighborhood size. Okay, so how many like intervals you want to decide, you want to divide the whole like data to, right? The network. And another approach actually was proposed by the Zhong and Levina and Zhu in Biometrica 2017. So this is more like statistical journals. And so basically here, they just define the neighborhood as the common neighbors. So if two people and they have a common friends, okay, so you have one set of friends and the other people, they also have the friends, the same set of the friends. And so you guys can be defined in the same neighbors. Okay, so here also like, you need to define the neighborhood size, like how big of those neighbors, right? And if the neighborhood size is a whole, like a whole network, so basically this reduced to the first model, the model that with a common p, okay? And so here we have these two examples, okay? And so like what I said, that the size of the neighborhood actually is a key factor to decide, to affect your estimation. So here we also did some like simulations which show you that it's indeed actually affect the estimation results like significantly. Okay, so for example, this one here, this is a true graph or the true network, the true Graphon model actually, and so we are using to generate the graph, okay? And so we generate the graph from this model here, this true like underlying probability, and then here the upper one here is actually use the sort and the smoothing method, and the bottom one is a neighborhood smoothing method. Okay, and for the sort and the smoothing method, so we here define this like a neighborhood size is 2, 10, and 50. So we let it vary like from 2 to 50. And for the neighborhood smoothing, we let this like a neighborhood size vary from 0.5 to 5. Okay, and you can see that if h equals to 2 here, and it significantly undersmooths the results, right? And so you see that it's not like the community or the boundaries here is not clearly separate. Okay, so this estimate is better compared to this one. However, for this one, so it's overly smoothed. Okay, and the overly smoothed basically means like it's too smooth, and which means that the neighborhood is too big. Okay, the neighborhood is too big. And so similar thing happens here. So this one is actually, you see the pattern, but there's also like a lot of noise, right? And this seems to be okay. And this is just too smooth. Okay, and so this one here, this example or simulation just tell us that basically the neighborhood size actually is a key factor that affect the the estimation of the prediction results. Okay, and then how to select that which one is the appropriate like neighborhood size. Okay, so how can we just tone the the hyperparameter and to make a good estimation. Okay, and if we have independent data, that people always know that we are using cross-validation, right? And so even in the neural network, in the deep learning, and the people use a cross-validation, so basically select the the tuning parameter lambda here, right? However, the difficult thing for the doing the cross-validation for the network is network basically have a two component. One of the component is node, and the other component is edge. Okay, so whether we want to split the node or split the edge. Okay, so it's not like the independent data will only have one number. Here we have two things to represent each entity. Okay, and suppose we are doing the node splitting. Okay, we are doing the, so for example, like if we have 5 nodes, and then we just doing the threefold cross-validation. So we split the data into the 3 different subsets, right? And each time we just take one subset as a test and give it using the rest of them as a training, right? So for example, if for the fold one, so we use this as a training and only have the last subset, this like number 5 as a testing. Okay, and so if we only use a training with the edges for the training, okay, obviously the distribution of this one here is completely different from the distribution of this one here, right? And the model estimated from this is also not the model estimated from this. Okay, so this basically here we cannot just use this to train the model and then do the validations, right? Because the essential thing for doing the cross validation is the subset have to have the same distribution as the full set of the data, okay, and which cannot be held here. And recall that actually for the Graphon model, we assume that each of the link independently, not identically, but independently follow the Bernoulli distribution, right? So here a keyword is independently. So naturally, we can just think that we can do the edge splitting because the edge, they are independently distributed, okay? And so for doing the edge splitting, and so we just pick up the different node pairs. Okay, so suppose we have an n node, and then we have the n times n minus 1 divided by 2 edge pair, right? And so we just put those edge pairs and into, into a vector, and then randomly sample some of the node pairs. So for example, this one here, and we randomly sample those node pairs. So, and so basically we just sample the edge. Okay, and we can, we can use basically the sampled edge here as the validation set, and using the rest of them here as a training set. Okay, and so sounds like we solved the problem. However, here, if we look at this training set here, the training set have some of the missing values because we removed those one here, right? And so the originally like this distributions still a little bit different from the full data distributions, right? And then what can we do? What can we do? So because like for the cross validation, so basically we just get estimation from this training set, right? And naturally that, or a simple or naive thinking of this is we just plug in 0 here, right? Plug in 0. However, if we plug in 0 and if we sampled like many of those like data here, and it will just amplify the effect of the no link, no link probability, right? So for no link probability, you have a in other words, for the no link thing, and you have more data to estimate the 0 compared to the data estimate the 1, right? And so for this Bernoulli distribution, then basically, for estimate the 0, you have because we have more data and the variance will be smaller, right? And the probability of estimating the 1, then the variance will be larger, okay? And then we are thinking that maybe fill in 0 is not probably a good idea. Then what else we can fill in? Okay, so actually there is one of the approach. The approach actually, this approach was developed by the Li and the Lavena and Zhu basically They published in the Biometric 2020. So they are doing the edge cross validations. And so this number here, they basically use a matrix completion approach. So to fill in those like numbers. Okay, they treat those in here as missing values. Okay, and so actually the best estimate here, ideally, if we know the PIJ here, the underlying PIJ here, right? And so we can just draw like a, or flip a coin, actually to see whether it's a head or tail. So based on this underlying PIJ, right? However, here we do not know the PIJ. Okay, so for their approach, they just impute this missing value use matrix completion. This method, okay, so they employed a low rank matrix completion technique to impute the missing values. In particular, they first fill all the missing entries with 0, then use a single value decomposition thresholding procedure to construct the low rank approximation A tilde matrix. And then they use the A tilde matrix for the Graphon estimation. Okay, and the threshold here is a hyperparameter here, of course, right? And then the whole algorithm requires n-cubic computational cost, which is very expensive for the large network. Okay. So any question for this so far? Okay. Well, let's move on. So the basic idea is, they impute those numbers using the low rank, like a matrix completion approach. And then, for this low rank matrix, and they denote as A tilde. And they use A tilde, so basically estimate this like a network. Okay. And so what is going to happen if we do not impute the missing values by the PIJ, but common probability P? Okay, so because the previous one, if we want to impute basically the estimated PIJ, so it's need an n-cubic computational cost, right? So here we don't want to impute this PIJ, okay? But we just impute some common probability P. Okay, so as the ergodic model, so it's just a P. Okay, and for example, if we use the first fold for the validation, so we have this like a missing address. We have this missing address, and so we just fill in those missing addresses with the P. So we first get an estimator for the average connecting probability, which is an average of all PIJs. And so it's pretty much just the density of the network. So we calculate this like density of the network, total number of connections over the total number of entries. Okay, and we denote the PIJ, and we impute this like missing values with this like average probabilities. Okay, so it's very easy to prove that the network density is unbiased estimator for the average connecting probabilities. And the network density actually calculated the ratio of the observed edge to the number of possible edge. Intuitively, this count the proportion of the right entries, and in this example, D is 6/10, since there are 6 edges in total and 10 possible edges. Okay, and then we just use a Bernoulli 6/10 to denote random numbers to impute these missing entries. Suppose we randomly generate the fake edge from the Bernoulli distribution, as shown in the slides here. Okay. Yeah, Bernoulli D. Okay, so they use. So now we have this like a the fake generated edge. Okay, And then we do the same procedure for the fold 2, and we have the fold 2, the fold 2 like a fake edge, and we also have the fold 3 fake edge. Okay, so we have the complete the training set 1 and the complete the training set fold 2, complete training set fold 3. Okay. So now we fill in the number. However, we know that here the estimation must be biased, right? And because we didn't fill in those like missing values with the true Pij here, right? But we fill in with some like a biased number, biased estimation. Okay, and then what can we do? We have to correct this bias, right? So how can we correct the bias? So the Aij here basically have two of the parts. So one of the part is the true edge, and the other is actually the fake edge. Okay, so for the true edge, okay, it just follows the original distribution, but for the fake edge, so if I and j are in the validation set, which means that in the training set, and they must be connected by the fake edge, right? And they follow this Bernoulli distribution. So with a common like a fill-in probability d. D here is basically, sorry, d here is this one here, right? And suppose that we just divide this like an edge and into the k, into k fold. Okay, so for each fold we have an equal number of edges. Okay, and then the probability for I and j in the validation set is 1 over k. Okay, and then this one here, given I and j in the validation set, is actually, this probability is d, right? And so basically we have these probabilities. Okay, and so here k is the number of fold, and if ij are not in the validation set, then it just follows the original Bernoulli distribution with the probability Pij. Okay, so we have that the probability P and J are not in the validation set, and which have this probability, and also the if ij are not in the validation set, and there is an edge, the probability for having an edge is a Pij. Okay, so here by the law of the total probability, we have that for each entry here, the connecting probability, so Aij tilde equals to 1, have this probability. Okay, so follow this probability. Now in this probability, D is known, K is known. Okay, so the only unknown thing here is the Pij. Okay, so this is estimable from the training set, right? And so this estimable from training set, this is known, only this are known. So we can solve this equation to get estimation for the Pij. Okay. So basically solve this equation, reverse this mapping, and we have the Pij hat, which follows, have this explicit form. Okay, so this form can be used to correct the bias we generated when input these missing values. Okay, so here we have the bias correction step. Okay, and the Pij hat tilde is basically the estimated Pij from the training set. Okay. After getting the unbiased estimator p-hat, we then extract the p-hat entries of the validation data. We then calculate the mean square difference, between the observed Aij and the Pij hat in this like a validation data. The smaller difference basically here indicate that the better estimation, right? So this is similar as the other cross-validation approach. Okay. And lastly, we can build the theoretical properties of our method. We need to impose to to get these results, basically we need to impute the two assumptions. Firstly, we require that the number of fold k should have the same order as the number nodes n. So both of them, increase at the same order. This means that as n increases, the number of fold k also need to be increases. Okay, actually leave one out is an example that satisfies these conditions. Okay, leave one out like a cross-validation. Secondly, we require that the estimator difference norm and the adjacent matrix difference norm have the same stochastic orders. Basically, we require that the smaller change of the adjacent matrix should lead to the smaller change of the Graphon estimator. Okay, and we empirically show that the Graphon estimation method satisfies these assumptions. And so this is actually, in most of the real practice, this is a really mild conditions. Okay, under the above two assumptions, given a set of the hyperparameter, we can theoretically prove that our method can select the optimal hyperparameter asymptotically. Okay, so recall here we basically define the one that minimizes the mean square error as optimal, like hyperparameters here. This basically means that as long as the network is large enough, and we can select the best hyperparameters. Okay, so here in summary, compared with the edge cross-validation, and we do not impose the low rank assumptions, or we do not use the the cost the very costly matrix completion algorithm. Okay, and we do not introduce additional hyperparameters, and we will show that our we will show that our method is much faster. Okay. Here, to show that actually we indeed got this optimal tuning parameter, we conducted some simulation experiment to show the performance of our method. We use automatically turned on. We use the Graphon model, basically. Yeah. So, what? Hello? Yeah. Okay, it works. So we use a Graphon model to generate the network data. First, we generate a latent position for each of the nodes by drawing from a uniform distribution. Then we employ the four widely used smoothing functions to generate the connecting probability Pij. Then we use the Bernoulli distribution to generate Aij. Okay, and the probability matrix, the true probability matrix, is shown in this column here. Okay, so the actual function, the generating function for the Graphon function is shown here. Okay, and here we show an example of the network under this the generated network under this four settings. Okay. And we also use a different number of nodes. We increase the number of nodes from the 50 to 200. And in this simulation setting, we set the number of fold k as a proportion to n. So it's basically k equal to 0.1n, so almost tenfold. Okay. And so here I just show you some of the results. Okay, so this column corresponding to 50 nodes, and 100 nodes, 150 nodes, and 200 nodes. Okay, and so here we let this like a hyperparameter vary from 0 to 6. Okay, so it's 0 to 6. And so here the blue line here is basically the best, the true MSE. Okay, the assuming that we know the the true PIJ, assuming we know the true underlying models, and so this is actually the best situation. This is the MLE. And the red line here shows that our Graphon CV score. Okay, and you can see that basically, the true MSE and our Graphon CV score basically minimize that the same value, the same hyperparameter here. Okay, and so the bottom one here is like are very close to each other. Okay. So we then compared our method with the edge cross-validation approach proposed by Zhu Ji's group in 2020. Okay, and so we basically here we visualize the true probability matrix and the estimated like a probability matrix that is obtained using the hyperparameter selected by the our approach and the edge cross-validation approach. Okay. As what we can see from this graph, actually the estimators in the second column looks like similar to the truth, and the estimator in the third column either have the under smooth problem or the over smooth problem. So the third column here, this one is selected by the ECV, and this is actually selected by our method. Okay, so here, basically, the pattern we selected, like, the Graphon estimated is more close to the true situation. Okay. In addition, here we compared the time, the computation time of our approach with the, the ECV approach. Okay, and our approach is actually the red curve, and the ECV approach is a purple curve. And as we can see that our method have much smaller computational cost. And this is because that when imputing this like a missing value, we do not use a matrix completion, which is actually very time consuming. Now let's take a look of some like real applications of our proposed method. Okay, so as what I have said, that developing a new drug need to go through these procedures roughly like 12 to 15 years. Okay, and the cost for developing a new drug is usually like $2 to $3 billion. Okay, and this is really time consuming and expensive. So then, a popular approach is actually repurposing already approved drugs. And so this is an idea for the drug repurposing. Drug repurposing is especially useful for conditions where the treatments are desperately needed. So for example, when there's like a pandemic, so the COVID-19 pandemic, right? And we are actually in urgent need of the drug to treat COVID. However, it is nearly impossible to develop a new drug, which take like 12 to 15 years long. To treat it, okay? And there's many successful examples for the drug repurposing. And here I'm just show you that one of the, the thing that we have obtained based on our like Graphon CV approach. Okay. A very popular way for the drug repurposing is just to predict the new drug and the disease relationship between the, based on the knowledge graph. So usually knowledge graph can just predict the biological relationships between drugs, disease, and the possible genes. And based on this graph, we predict the new link between the drugs and the disease, and this prediction found a new use and for the old drugs. Okay, and this depends on two key steps. The first step is construct the knowledge graph. The second step is predict the new drug, the new disease drug link. Okay, based on the knowledge graph. And if you are here actually last year, and so last year basically I introduced this like knowledge graph construction approach, which called the MyReader. So MyReader is basically just a robotic like a learning system. So it can just automatically read all the publications deposited into the PubMed and during certain time windows. So for example, this one here, from this time to this time, everything related to COVID-19 will be read. Okay, and after read those like articles and using the natural language processing tools, and so we can construct this like disease and the drug networks. Okay, this is a brief introduction. So for the MyReader, so basically we have those like publications, right? And we process the publications through using this like ALP approach. Okay, and then we classify those entities into the disease group, genes group, and the drug group, and then we construct the cross category like a co-occurrence network. So this basically means for this two here. So for certain drug and the disease, okay, so if they co-appear at the same articles, and then we will just count one of the co-occurrence. So based on the number of co-occurrence, we construct this co-occurrence network here. And this is essentially just the knowledge graph obtained from the MyReader. Okay, and so here is the output from the MyReader. Okay, and in this network here, and we have 1036 nodes and this much of the edge. Okay, and using this ECV approach, and then we got the neighborhood sets. So both of the like the estimation approach here we considered is always the neighborhood smoothing approach. Okay, as it has a less strictly requirement compared to the sort and smoothing approach. Okay, so using the neighborhood smoothing approach, and so basically here we select the hyperparameter using the ECV approach, and this red one here is we select the parameters using our Graphon cross-validation approach. Okay, and you can see that actually using our method and the optimal tuning parameter is 1.2, which is here, right? Have the smallest score, and using ECV approach is actually here, and is 0.2. Okay, and so like because the vertical here, the vertical line, the y-axis here is basically the score value, and so we are using different scores. So this basically not a does not matter at all. Okay, the matter thing is here, like the location of the bottom. Okay, the location of the bottom. So one of them is 1.2, the other is 0.2, and then which one is better, right? That is a natural question. So how to see which one is better? Let's first take a look of which one is better, then I show you the real meaning of that. Okay, so basically this one here is using the one that we have using the tuning parameter we have selected, so it's 1.2, and this one here is using the 0.2, which is selected by the ECV, and this vertical this axis here is actually indeed manners because it indicates the accuracy. Okay, and so it's basically that indicates the proportion of the correctly predicted link. Okay, correctly predicted link. And you can see that for the accuracy, and so, you know, the x-axis here is actually the number of the top, you know, the link with the top connecting probabilities, okay? And so, for example, this is the top 10 probabilities, and 2 here is the top 60. And you can see that our method actually, you know, completely beat this ECV approach. And so the computation time, actually, we also have a much more shorter computational time. This is only that much, and this is computational time for the ECV. Okay, and now, like scientifically, like you know, why our method makes sense. Okay, so this is basically the top one that we have selected with the highest like link probability 0.91, right? And this is the drug here is called the ladipasvir, okay? And so basically ladipasvir, so, you know, based on the study that we have, you know, based on the estimation like the data that we have to train this like you know, to make this prediction. And so we predicted that this has a high risk probability. And later on, basically, we validated this actually with the, you know, the future publications, okay? And we found out actually this one here, this drug originally was used to treat the hepatitis C, but later on, actually, it was approved to treat COVID-19 here. Okay, so it's indeed helped with this, like you know, COVID-19 disease. Okay, so here is basically the time window that we used to make this prediction, and this is the, you know, publications that we used to validate, not validate as a testing set. So this is a test whether, you know, our prediction is correct or not. Okay. And so we have pretty much everything. And so I want to thank my lab. And also this work particularly was done by Hui Min, who is sitting there. So if you have any question, don't ask me, ask her. She knows better than me. Okay, any question?
Yeah, I'm wondering, your results can be extended to directed graph, since your talk is talking about the normal graph. Yeah.
Yeah, exactly. So here, basically, I didn't consider the, you know, I only consider this like, you know, no direction like a network, but actually it naturally generated to the directional network, because so here the true situation is basically, you know, we propose here is how we split this like into the training and you know, training and the validation. And this is actually, you know, the key like a part, so key part of my work. And so whether we split the directional network or indirectional network is actually doesn't matter. Okay.
Any question?
You probably have to use it.
Okay. So thank you for the wonderful talk. I just wondering, like in your data set, not this particular data, but if some data set you have something like latent classes which you don't observe, and these PIJs, those probabilities for different classes, maybe they are not exactly same, they are not exactly different, but they are similar in some sense.
Yes.
So how do you handle, in that case, I mean, you will have some kind of clustering or something, because these PIJs are comparable. So in that case, how do you handle this problem?
So you are asking that, you know, my training and the full set actually are similar.
That's right.
And but not exactly
Not
the
exactly
same.
same, not exactly different, but they are similar in some sense. And the level of similarity also differs from one group to the other.
Well, actually here, you know, we don't assume actually our training set and the original network have the same distribution. Actually, we know that they have, after the imputation, they have a different distribution.
Yeah.
Okay.
So you are assuming that they have different distribution.
Yeah, we assume it, right?
So,
and but like we know the difference between these two distributions, but we have the correction part. So we use the biased estimator. We know we made a biased estimator using the training set.
And
Okay.
then you are adjusting that bias.
Right, we're adjusting the bias. Okay, like if we know that actually, for example, like what you said in your situation, so it's pretty, I think it's not really, you know, cross-validation, right?
Mm-hmm.
Because you know the distribution for the other network,
That's
right?
That's right.
And so if you know the distribution for other network, and then basically you can also derive or you can calculate the bias. And so basically you can make the bias correction. And I guess that you know, more like probably more relevant situation is how you measure this like distance between two different networks, right? Yep. And so there's also some of the ways. So you know, you need to consider whether you have the labeled network or unlabeled network. If you have a labeled network, then basically using the Wasserstein distance, right? Wasserstein distance is one of the way to measure the difference between those two things. Because network, you can consider that as a Zhong distribution, right? So distribution to distribution, so you can use the Wasserstein distance, right? Measure just like how close this network are, or how similar those two networks. And if you have undirected network, then that's a purely, you know, you classify this network based on this topology, right? And so you basically consider all the subgraphs topology, all the different topology structures the network have. Okay, so you basically can just get this like distributions for the subgraph or the topologies, and compare this like whether how similar these two distribution with each other. So this probably related to the equivalent class thing. Yes.
Okay.
Good question.
Yeah. Thank you.
Other question? No? I guess I can.
Well, thank you, Professor Zhong.